9.10 Lesson 5, Taylor and Maclaurin series. Our objective for today is to find the first few terms of the power series for functions that are products of the elementary functions listed on page 682 or quotients of the elementary functions listed on page 682. So these are the power series we have for the elementary functions listed. And we've been working with these. For example, we have here the power series for sine of x, and we were able to use that to find power series for functions like sine of x squared simply by taking the x squared and replacing every single x in the power series for sine x with x squared. So today we're going to take the power series that we have on page 682, and we're going to be using them to find the first few terms of the power series for functions that are products of these or quotients of these. For example, today in one of our examples, we'll look at the function that is going to be the product of each of the x, and we have a Taylor series centered at 0 for each of the x listed here, and arctangent of x. And we have a Taylor series centered at 0 for arctangent of x. But if we multiply these two functions, how can we get a power series? The only issue here is that each of these functions is represented by an infinite Taylor series. So you need to try to figure out some kind of a pattern, or just settle for the first few terms of your infinite series for the product of the two functions. To have a better understanding of what I just said, we'll review how to multiply polynomials. You see this problem and you think, yesterday math was such an easy game to play. And it's true. This is something that you can do easily, and all you have to do is use the distributive property. Now, many students are accustomed to multiplying polynomials by using the distributive property in a horizontal format. So you would just take x cubed and multiply it to 2x squared and 3. You would take 2x and multiply it to 2x squared and 3. And you would take 9 and multiply it to 2x squared and 3. And then you would combine like terms. That's certainly one way of doing it. There's another way you can set up the multiplication, and we're going to go for the other way of doing it, because what it does for us is it lines up like terms so that it's easier for us to identify like terms and it's easier for us to combine like terms. It's doing the same thing, but just setting it up in a vertical format for the multiplication. So if you want to do the same problem, but you want to set it up in a vertical format for multiplying the polynomials, you can write the first polynomial expression on one line and the second polynomial expression on the line below that. And you can line up the terms that have the same power. So that's what I've done. And if you're missing a particular powered term from each expression, you can either write 0x squared, for example, for the missing second degree term from the first polynomial expression, and 0x for the missing first degree term from the second polynomial expression. Or you could alternatively just leave that blank. So either way is fine. So what you want to do now is the same thing that we looked at earlier for the horizontal format of multiplying polynomial expressions. You're going to use the distributive property. So if you were to do it horizontally, I showed it one way, but it's the same thing. You would, for example, take the 3 here and multiply it to the 9, to the 2x, and to the x cubed. That's what you would do if you're doing it horizontally. I showed it differently earlier, but it doesn't matter. But the idea is you're using the distributive property. And then you would take the 2x squared and you would multiply it to the 9. to the 2x and to the x cubed, and then you would combine like terms. We're doing the same thing now. We're just organizing it in a vertical format. So we're going to do 3 times 9, 3 times 2x, and 3 times x cubed. And that would give us 3 times 9 is 27. And then we have 3 times 2x is 6x. And notice that I write the 6x in the same column as the 2x. So I'm writing terms with the same power in the same columns. So now we have 3 times x cubed, which is going to be 3x cubed. And then I'm going to multiply the 2x squared to each of the terms from the other polynomial. So we're using the distributive property. So 2x squared times 9 is going to be 18x squared, and I'll write that here in the column for second degree terms. And then I have 2x squared times 2x, which is going to be 4x cubed. And then I have 2x squared times x cubed, which is going to be 2x to the 5th power. And we will add like terms. So the good thing about having it set up in this way is that your like terms are already lined up. So I just have 27, I have 6x, I just have 18x squared, and 3x cubed plus 4x cubed will give 7x cubed, and then here I have 2x to the 5th. So it's just an alternative way of setting up the multiplication, but it will come in handy for the types of problems that we want to do for today's lesson. Example 7, Part A, find the first 3, so we just want the first 3 non-zero terms in each of the Maclaurin series. So there's a Part B, and for Part A we have e to the x times arctangent of x, and we have a different function for Part B. So find the first 3 non-zero terms in each of the Maclaurin series. As we've already discussed, what we're going to do is we're going to use the Taylor series centered at 0 for e to the x, and the Taylor series centered at 0 for arctangent of x, and each of those series has infinitely many terms, and we'd like to multiply them, similar to what you just saw with the polynomial multiplication. But of course, each series has infinitely many terms, so all we want to do is just get the first 3 non-zero terms in the product of the two series. So here we have the Taylor series centered at 0 for e to the x, and then here we have the Taylor series centered at 0 for arctangent of x, and we'd like to multiply these two Taylor series. Again, make sure you recognize that there are infinitely many terms in each of these Taylor series. So now we're going to multiply these two Taylor series, much like we did with our example from algebra earlier. We're going to use a vertical format for the multiplication. So here I have the Taylor series centered at 0 for e to the x, and for the second line I have the Taylor series centered at 0 for arctangent of x, and we'd like to multiply them together. So the way you do that is you're just going to multiply each term of one series to every single term of the other series. Now you can't possibly write everything out because there are infinitely many terms in each series. But remember the instructions for this problem. We just want the first 3 non-zero terms in each of the Maclaurin series in the first example for e to the x times arctangent of x. So although there are going to be an infinite number of products that you'd have to calculate, you don't really have to do that because you just want the first 3 non-zero terms, starting with the lowest degree term and then like 2 more after that. So if you multiply x times 1, you get x, and I can write that under in the column for first degree terms. If you multiply x times x, you get x squared, which I will write here in the column for second degree terms. And x times 1/2 x squared would give me 1/2 x cubed. So I'm going to write that here in the column for third degree terms. X times 1/6 x cubed will give me 1/6 x to the fourth. And I'll write that in the column for the fourth degree term. And so on. I don't really need to worry about what comes after that for now, because the next thing that I want to do is go to, and of course, as I said, so on. So this actually keeps on going forever, but we can't do that. And we're only interested in finding the first three non-zero terms in the product of e to the x and arctangent of x. But what I've done so far is not enough, because you do have to think about what other terms you have in the power series for arctangent of x. And of course, there are infinitely many of them, but we want to look at negative 1/3 x to the third power. You know you need to multiply that to each of the terms of the power series for e to the x. So I'll see what I can do here. And negative 1/3 times x cubed is going to be negative 1/3 x cubed times 1 is going to be negative 1/3 x cubed. And I'm going to write that in the column for third degree terms. And then I have negative 1/3 x cubed times x. That's going to be negative 1/3 x to the fourth power. And then I have negative 1/3 times negative 1/3 x cubed times 1/2 x squared. That's going to be negative 1/6 x to the fifth. And of course, it just keeps going after that. There are infinitely many terms. I probably want to list one more term from the first line, and you'll see why. So in the first line I had x times 1, x times x times 1/2 x squared, x times 1/6 x to the third. Well, maybe I don't really need to, but let me just go ahead and do it. So I have now x times 1/24 x to the fourth, which is going to give me 1/24 times x to the fifth. I don't think it's really needed, and we'll see when we work with the next line why that is or why that isn't. So if you want to now go to the next term in the Taylor series for arctangent of x, it would be 1/5 x to the fifth. And you're going to multiply that to each term of the Taylor series for e to the x. If you do 1/5 times x to the fifth times 1, 1/5 x to the fifth times 1 is, of course, just 1/5 x to the fifth. And then if you have 1/5 x to the fifth times x, that would give you a sixth degree term, and there'd be infinitely many. But one thing that you should notice is that the next term after 1/5 x to the fifth from the power series for arctangent of x is a seventh degree term. And when you start multiplying that seventh degree term to each of the terms of the power series for e to the x, the lowest degree term that you can have, it would be seventh degree. So I'm not going to get any more fifth degree terms ever again, even if I were to continue this for the rest of eternity, right? The next degree term from the power series for arctangent of x is seventh degree. So the lowest degree term that you can have from multiplying negative x to the seventh over 7 to each term of the power series for e to the x is seventh degree. And even if I were to continue this process forever, I'm not going to get anything that's fifth degree or less. So this is all I will have up to the fifth degree. And if I add the like terms, which are already lined up, I will have x plus x squared. And then I can add these two like terms, and I will have I will just need to add the leading coefficients. 1/2 plus negative 1/3, and you need a common denominator of 6. And that would give you 3 over 6 plus negative 2 over 6, which is going to give you 1/6. So you will have 1/6 x cubed. And I could actually keep going here. If I add the two like terms here by adding the coefficients, that would give me 1/6, negative 1/6, negative 1/6 x to the fourth. And if I add the three like terms that I have here by adding the coefficients, I would get 3 over 40 times x to the fifth. And I'm actually confident that these are the correct first 5 terms of the Taylor series for e to the x times arctangent of x, using the logic that I shared earlier, which is that the next term from the Taylor series for arctangent is 7th degree, and if you multiply that to 1, you will get a 7th degree term. So this is the first 5 terms of the Taylor series for the product of e to the x and arctangent of x, the Taylor series centered at 0. The problem is only asking us for the first 3 non-zero terms, so you can just list the first 3 non-zero terms, and you would be done with that problem, which was find the first 3 non-zero terms in the Maclaurin series for e to the x times arctangent of x. So before moving on, there is an edit that I need to make. We multiplied x times 1 over 24 x to the fourth, and that gave us a 5th degree term here, and it would be 1 over 24 times x to the fifth. Here we have a second example. Find the first 3 non-zero terms. So we just want the first 3 non-zero terms in the Maclaurin series for tangent of x. You would begin this problem by recognizing that tangent of x using an identity from trigonometry, it's called a quotient identity, is sine x divided by cosine x. And of course, this helps us because we have Taylor series centered at 0 for both sine x and cosine x. So here we have the Maclaurin series for sine x, and here we have the Maclaurin series for cosine x. And we'd like to take the Maclaurin series for sine x and divide it by the Maclaurin series for cosine x. So how would we do this? We would remember how to do polynomial long division and apply that algorithm. So here we have a quick review of polynomial long division. So here's an example problem. Our dividend is 2x cubed plus 8x plus 3, and our divisor is x squared plus 4. So how do we write the answer? We're going to find the quotient, which we will write, plus the remainder over the divisor. So what is the algorithm? How do we do this? The algorithm is as follows. You take each term from the dividend and divide by the highest degree term from the divisor. 2x cubed divided by x squared will give us 2x, and you would write that here. Multiply that to the divisor. That would give 2x cubed plus 8x. And then you would subtract and that would give us 0, bring down the 3, and you can't go any further than that. That's as much as you can do. So this is our quotient, and 3 is our remainder. So we're going to write 2x cubed plus 8x plus 3 divided by x squared plus 4 is equal to our quotient plus remainder over divisor. So to find the first 3 non-zero terms in the Maclaurin series for tangent of x, we'd like to divide the Maclaurin series for sine x by the Maclaurin series for cosine x using the long division algorithm that we just saw. But of course, each of these series are infinite series. So in the long division that we just saw, we wrote the dividend and the divisor in descending order of degree. But we can't do that here because each of the series that we have for sine x and cosine x have infinitely many terms. We can still apply the same long division algorithm, but we will have to write the divisor. We would have to write the dividend and the divisor, both of them in ascending order of degree. So here I have the first 3 terms of the Maclaurin series for sine x, written in, of course, ascending order of degree. And for the divisor, I'll write the first 3 non-zero terms of the Maclaurin series for cosine x in ascending order of degree. 2 factorial is 2, and 4 factorial is 24. And of course, they are infinitely many, but I don't really need to write more than this, because in the instructions, all I'm interested are the first 3 non-zero terms in the Maclaurin series for tangent x. So we apply the same polynomial division algorithm that we saw earlier. So we would take a term from the dividend and divide by a term from the divisor. But earlier we took the highest degree term from the dividend and divided by the highest degree term from the divisor. 2x cubed divided by x squared to give us 2x. Now we're going to do that, but with the lowest degree term from the dividend divided by the lowest degree term from the divisor. X divided by 1 will give us x. We will write that above the x column, above the first degree term column for the quotient. And just like before, we use the same algorithm. We're going to multiply the x to each of the terms from our divisor. And that would give us x times 1 is x, and then I have x times negative x squared over 2 would be negative x cubed over 2, which I can write this way. And then I have x times x to the 4th over 24, that would be x to the 5th, and I have 1 over 24 here. And of course, it would keep going, but I don't really need to worry about this because, again, all I want is the first 3 non-zero terms in the Maclaurin series for tangent. But I need to continue with the algorithm, which is to now subtract. So when I subtract, x minus x is 0. And if you subtract negative 1/6 x cubed minus negative 1/2 x cubed, that will give 1/3 x cubed. And then if you subtract 1 over 120 x to the 5th minus 1 over 24 x to the 5th, you'll get minus 1 over 30 x to the 5th. And of course this goes on, but I don't really need to worry. Again, because I only want the first 3 non-zero terms in the Maclaurin series for tangent of x. And I already have the first non-zero term, and I just need 2 more. So I continue with the algorithm. Now I would take the lowest degree term from this line and divide by the lowest degree term of the divisor. And that gives me 1/3 x cubed, which I will write here above the third degree term column, 1/3 x cubed. And then I continue with my algorithm. I would need to multiply the 1/3 x cubed to each term from the divisor, and that would give 1/3 x cubed minus 1/6 x to the 5th, and so on. And when you subtract, continuing with the algorithm, what you're going to get right over here, I'm running out of room, so I'm just going to draw something in red and write it a little bit off to the side. I'll get 2/15 x to the 5th, and so on. And continuing with the algorithm, you're going to divide this term by the lowest degree term of the divisor, and that would give 2/15 x to the 5th. And I don't really need to do anything beyond that, because all I wanted was the first three non-zero terms in the Maclaurin series for tangent of x, and I already have the first three non-zero terms of the Maclaurin series for tangent of x. In today's lesson, we were able to find the first few terms of the power series for functions that are products of the elementary functions listed on page 682, or quotients of the elementary functions listed on page 682, and we looked at an example for each.